1.
Hello, my name is Mark Alonso. I'm 2.2, and the table group is P.2G.4.
Hello, my name is Maxil, and my bio ID number is 2.11.
I'm Gabrielle Fregosa. My bio ID number is 2.7.
This is Chad McCarthy, 2.21.
And I'm going to get us started on the central dogma. So if you come closer, here's the central dogma. It starts off with DNA. And the process in which DNA is replicated is called DNA replication. From DNA to RNA, or more specifically mRNA, this process is called transcription. We'll put trans C for short. From RNA to proteins, this process is called translation. And this overall process with the DNA replication, DNA from RNA to RNA, RNA to proteins, is called the central dogma. And then we'll move over to DNA.
Replication.
No,
not
DNA,
yet.
just DNA.
DNA structure.
Just DNA structure. Here we see it's a double helix, but usually it's winded up. But for simplicity's sake, we have it straight. The backbone is made out of a phosphorus group, and a 5-carbon sugar, which is connected covalently, and it is also connected to a nitrogenous base, which is connected to the antiparallel, nitrogenous base from another side of the DNA, which is connected through hydrogen bonds. The 5' end is connected to the phosphorus group, and the 3' end is connected to the end 5-carbon sugar. And that is all. I'm going to go to DNA replication with Max.
Hello, my name is Maxil, and we're going to jump into DNA replication. So first, helicase comes along and begins unwinding the DNA strand, or the double helix DNA. While it's doing this, topoisomerase is here on top, or above it, or in front of it, however you look at it, and it basically makes nicks in the double helix so it does not become too tightly wound or overwound. It then replaces and kind of heals those nicks to prevent permanent damage later on, and that's its job. Helicase then just continues down the double helix strand, and now comes in DNA polymerase primase, but before primase, the binding proteins bind to either strand of the DNA that is now separated and keeps them from reforming and reconnecting together. Then primase comes in and it adds a primer onto the, we're going to say this is the leading strand, 3' to 5' down. From here, DNA polymerase 3 comes in and adds the nucleotide bases to the new strand, or what will be the new strand for this DNA. Then DNA polymerase 1 comes in and it removes the primer and replaces it with a nucleotide. And that is covering the leading strand. From here, we move on to the second strand, the lagging strand. This lagging strand is also, first comes in, once again, primase, and puts on primers. Except instead of just there being one on the beginning of the DNA strand, it is every 3, and these are known as Okazaki fragments. And basically this is why the lagging strand is a little trickier to code for, because DNA polymerase comes in and it starts putting down the nucleotides once again, like in the leading strand.
In the 3' to 5' direction.
Exactly. And it does the same thing. And DNA polymerase 1 then comes in and fills in and takes out the primers and replaces them with nucleotides, such as before. From here, the new strands kind of separate. Ligase comes in before that happens, though, and it fills in the gaps that are remaining, and then it connects the DNA strands into a double helix shape. From there, the DNA double helix is separate, making two new double helixes, one containing the parent old strand and one containing a new strand. And now we move on to Gabriella Fregoso with transcription.
Okay, so there's a certain sequence at the beginning of the DNA called the promoter, and transcription factors are put on top of the promoters, and it helps the RNA polymerase bind to the DNA strand. RNA polymerase puts the first nucleotides, which is the start intron. Start codon, sorry.
Which is the leading intron.
Which is the leading intron. You can speak. And then, as the RNA polymerase moves along the DNA, the RNA is then created. So then, during this process, as the RNA polymerase is moving, it's called elongation. And then when it comes to the very end, towards termination, the poly A tail is added to the end, and then the med cap added. Oh, okay. The poly A tail is added to the end.
Not yet.
What? What do you mean not yet?
Okay, continue.
Spicing first.
And then, oh wait, yeah, you're right. So, the termination signal sends away the DNA, and the spliceosome is sent in and cuts out all the introns. So first the
leading intron.
The leading intron is cut out, and then it's a blue box, right? And then all the introns are cut out. And then the spliceosome allows the exons to be bound to the other exons. So the excess introns are recycled, and then the spliceosome binds all these exons together. The poly A tail is then added along with the met cap to the very end, and the met cap allows for the mRNA to leave the nucleus. And when this happens, an enzyme called exonuclease comes and cuts the poly A tail. And it cuts it individually to all its pieces. Yeah. Then next we're on to translation.
With Shem Ricarte.
Moving on to translation. Sorry, give me a second. Oh God. I don't know the order. Whatever. Okay. So, moving on to translation, the new mature mRNA strand enters the ribosome. So the first codon will enter into the A site, which is the attachment site. This codon, which is AUG, is the start codon, which will code for methylene. tRNA, with its associated anticodon, will enter into the attachment site with its amino acid methylene. And this process continues. So the mRNA moves down again. The tRNA and its amino acid moves to the P polypeptide site, while the ribosome continues its coding. Sorry, some of these are out of order.
Creating an RNA transcript and adding RNA nucleotides.
So the next tRNA comes in with its amino acid into the attachment site. And again, this process continues on and on. So at this point, the tRNA moves to the exit site and leaves to pick up a new amino acid, while the new tRNA moves in and connects its amino acid to the previous one, creating a new polypeptide chain. This process continues on. tRNA comes in, then the previous tRNA moves to the exit site, comes out, tRNA moves to the polypeptide site with its amino acid, and the amino acid chain continues, and this process continues, creating a polypeptide chain. tRNA coming in, tRNA leaving to grab a new amino acid, tRNA moving to the polypeptide, amino acid binding to the polypeptide, and this process continues, bringing in tRNA, amino acids, tRNA amino acids, while the ribosome is moving down and scanning the mRNA. This process continues, and then eventually an amino acid chain, a polypeptide, is created, and this is a protein.
Okay, and then we move on to mutations with Marco Anzo.
All right, hello, I'm back. So for mutations, I'm gonna I'll use this as a quick example. There's three main types of mutations that occur within DNA. The first type that I want to go over is substitution, and within substitution, a certain nucleotide is switched with another nucleotide. So it can be A is switched with adenine is switched with thymine, which at times could create differentiations within the DNA, but substitution is the least likely because multiple codons can code for for the same amino acid, and then that's substitution. Then we can go into deletion, which is when one nucleotide is just deleted from the sequence of DNA. This can be harmful because it could throw off the structure and function of a protein, because we know that DNA codes for RNA and RNA codes for proteins and amino acids. And then the next one is insertion. Insertion is when it's like the opposite of deletion. Different nucleotide is inserted within the DNA sequence, which could also be as harmful as deletion because it could also harm the structure and function of the RNA, and then the RNA creates proteins, which could change its function, which could be harmful to the body. And those are mutations.
And what else could happen if the structure is changed? Could it be rendered
Useless? Or it could be harmful or useless, like it won't be able to do its job, or it could be doing the wrong job, or it could just be just doesn't do anything. So yeah, that's mutations.
And
Those are three main
also,
mutations.
could we have a visual example of the mutations?
That's a bit hard.
That's a bit, yeah, we already have it.
Okay.
Okay, that's
well,
it.
that's it.